Good evening. Today we'll be looking at physics informed neural networks. So the problem statement, physics is hard to simulate, and why is it hard to simulate? So there is a lot of computational cost going on because simulating that flow requires grid points, weeks of supercomputer time, that is the GPU. Then you have your mesh dependency, you have your inverse problems, and you have your data scarcity. So getting data for physics themed models is very difficult. Now that is we have the equations before of physics, and we have data of the data set, but there is no bridge between them. So what are physics informed neural networks? These are the type of deep neural networks which are trained to solve and discover partial differential equations, which is PDE, by using physical laws directly into their loss functions. So a standard neural network, it learns from the data itself, and physics informed neural networks learn from both data and physics. That is the kind of equation for physics based models. So what are some components and how is it different from standard neural networks and in physics informed neural networks? Like the training signal, you have just data loss here, but here it takes residual loss as well. For physical constraints there is none, but here you have the PDEs, that is the equations, and you have boundaries, that is in the equation boundaries and all. Data requirements, you have large labeled data sets for standard, but you can work with noisy data or sparse data as well for the physics informed neural networks. And generalization component, it is data driven only, but in physics you have physics constraint. Interoperability, it is black box, like you give an input, you give an output, you don't know what's going on inside. While in physics informed, you have the basic, like what it's going on, what concepts it is computing on, and your outputs will also be meaningful based on physics. Now inside basically the architecture. So the first step will be the network design, that is the deep network which has coordinates or spatiotemporal coordinates x, y, z and t as inputs and outputs. Then you have your auto differentiation using the autograd. The network computes the exact derivations of its outputs with respect to the inputs. The residual functions, that is the PDE residual, is computed randomly with collocation points. So the equation is given out here for that. You have multi-objective training after that, that is data fidelity or PT residual, boundary conditions, you can put your conditions, you can put your initial conditions, and you can be use optimization, like the most common one using Adam optimizer, which is like the most commonly used for fine-tuning and stuff, and in many kinds of neural networks as well. And the key applications is in fluid dynamics. So one such concept, which is the Navier-Stokes equations, governs all fluid motions from blood flow to jet engines, yet they are difficult to solve numerically. So some of the applications are like turbulence modeling, so PINNs can be used for like 3D visualizations of these measurements from sensors, which is difficult and almost impossible from the classical methods. You have your hidden physics discovery, that is given only the velocity data. PINs can reconstruct the pressures, that is like they can kind of make the pressure, make the points, like kind of visualize that using Seaborn and many other libraries. that were never measured directly. You have inverse problems, that is, you can identify viscosity, diffusivity, and you can directly learn from the observational data. You have the speed advantage. Once trained, the PINN is it orders the magnitude in faster than running a full simulation. It is faster, and you can use like GPUs of Kaggle itself for that, and you can benchmarks the results using the given using the research papers given, and you can check out like whether what the model is in the right direction or not. And beyond fluid dynamics, other concepts like heat transfer, you have structural mechanics, you have electromagnetics, you have quantum mechanics, you have drug delivery, you have climate science, you have geophysics, you have biomechanics. So there are many equations which can be put inside the model and can be used for training. So what are the advantages? So it can be run on sparse and noisy data. Data need not be complete fully. You have a unified framework for solving forward problems, inverse problems simultaneously. You have a mesh free. There is no grid generation in this, so it is seamless. You have continuous solutions, that is outputs are smooth. You have differentiable functions. You don't have any discrete approximations. And multi-physics, that is, you can use it in different field of physics like fluid or heat or structure. And what are some of the limitations? Training instability, so balancing multiple loss like functions, balancing multiple terms in loss is not trivial. Poor weightage, so you have to be very careful with that. Scalability, so scaling it will be a bit difficult because it does remain computationally expensive to train the model as and when you want to scale. Stiff PDEs, that is, problems, they are very vast and very different with time and length scales, so it is difficult to optimize. And hyperparameter sensitivity is like network depth, width, collocation point, distribution, which can affect the accuracy a lot. So there are variants of this. One of them which is HPVPIN, that is variational formulation using the test functions. You have the CPINN or the XPINN, that is for domain decompositions. You have DepoNet for operators, that is it generates solution maps, and rather than individual solution, it goes general. You have FNO, which is for Fourier neural operator, basically for Fourier equations. You have PINN plus transformers, you can use it for long range dependencies. You have Bayesian PINNs, which as the name suggests for Bayesian equations. And what are the breakthroughs from 2024 was that PINNs are solving real-time aerodynamic optimization. They can be used for cardiac simulation as well, just like for surgical planning. And they have climate modeling as well. Like NVIDIA has their Earth to digital twin platforms, they have made it using this PINNs. And what are the real world impacts? So which industry, who and all have adopted? So NVIDIA Modulus is one of the product of NVIDIA which they have used this concept. Boeing has started to use this for real-time aerodynamic shape optimization to visualize that. Biomedical as well, like for example blood flow or for cardiovascular design. It is used in energy sector as well for oil and gas. It is used for climate and weather as well, with twin platforms like Earth 2 by NVIDIA. So for entering the PINN, there are different types of frameworks using PINN, and who has developed them, what language is it in, what is it best for, like which areas it can be used. And this is like a sample of a snippet. As you can see, you are importing the model, which is deepxdsdd, Then you are defining your function, which is your heat equation, which we use Jacobian for that. You are uh, defining your geometry, your interval. You are defining your time domain. You are defining your geometrical time as well. You are defining your data out here, and you are defining your model out here. And as you can see, you have uh, setting up the model, you're compiling it, and you're training it, like iterations. Yeah, these kind of models you have to like at least use 1,000 epochs to get good results, and it is faster compared to the other neural networks. And um, it takes like a few hours if you are using the Kaggle's P100 GPU. I'll be showcasing a demo. The future, so the future of PINNs, that is, you have it can be used for simulating universal physics concepts. You can use multiple PDEs, you can use multiple domain skills like for GPT and all, but physics side of thing. And neural surrogates for digital twins, like for example, you can use this to check for entire factories or human organs. Basically, you can develop it more for more organs and stuff, not only for blood flow. You can use it for scientific discoveries. You can use it for quantum is like a part of each and every concept you can get. And you have an autonomous engineering design. Yep, you can use it for that as well. So the future vision is every physical system from individual cells to global climate will have a living digital twin powered by an AI. And this is projected for 15 billion by 2030 in various industries like aerospace, energy, biomedical, and climate applications. So what are the takeaways you can get from this session is that PINs unify data-driven learning with physics-based constraints. You have applications which span not only fluid, but you have structural mechanics, biomedicine, and you have the ecosystem is mature, that is NVIDIA is already using this. You have DeepXD, you have FNO, and you have advanced variants like DeepONet, XPIN, and Bayesian PIN, which addresses scalability and uncertainty. And there are convergence with the foundation models will define the next decade. So how can you guys also explore this? So you can explore DeepXD. You have their docs, you have NVIDIA Modulus, you can use that. You can use RISE. I mean, you have like the research paper by RISE, Perdicaris and Karnidikis with 2019. And you have the SciML community on GitHub and Discord as well to check even that. Yeah, my bad. So, uh, so I have used the coupled damped harmonic oscillation dataset out here. Why is it ideal? Because like it has two interacting masses for second order ODE. So what this notebook will learn. So the notebook, we will model two positions x1 and x2, which is a 2D, and we will enforce these equations for the damped oscillator, coupled damped oscillator. So we are importing our libraries like OS, gglob, matplotlib, panda, seaborn, scipy for periodograms, and Pearson R graphs. And we'll be seeing various different graphs. We have torch as well. We are using PyTorch, and we are setting the device as CUDA. And we will be training two models, which is a baseline and one is the PINN, to show the difference. One will run for 1200 epochs and the other will run for 1800 epochs, which is ideal for them. And we are defining the weights, and we are defining the ratios of the train test split, train test val split basically. And we are loading the data set out here and resolving all path issues so that the paths doesn't become a hindrance out there. So here I am cleaning the data, so I am replacing spaces properly, doing the spacing, and after that I am normalizing the columns so that it is easier for us to retrieve it. And there are some columns which might not be needed, so I'm removing them. After all that, this will be our final data set, which has the time, x1 v1 a1, x2 v2 a2, and system id. And since we don't want system id out there because we are looking at just one system in this, so I've just kept this a1 a2. Then we check for missing values, duplicate roles, time steps, and I plot a graph for time step, as you can see here. Then we plot the overview of all the series which is happening, that is position x1 over time, x2 over time, velocity over time, acceleration over time, and we plot distribution plots for each term, that is x1, x2, velocity 1, velocity 2, acceleration 1, acceleration 2, and density as well. Then we plot a correlation matrix which will tell us, that is the heat map, which will tell us the correlation between any two columns basically. And we are using phase portraits and coupling views as well to check. So you can see these phase portraits, like how the particle is oscillating basically the path. And you are checking out the rolling behavior as well, as you can see out here how close they are rolling, the decaying is going on, and rolling means velocity, volatility. And then we are analyzing frequency using periodograms. So it is more between 0 and 10 compared to the rest. Then we are seeing lag plots to see the lagging and all that stuff which is visible in these plots. Then you are seeing the chronological splits of train tests, like how is it split. So these legends will tell how to check the graphs, that is like the bigger one is the x1, the second one is x2, how it is distributed, the train test and validation. Then we are defining our base model, so which is an MCP model, MLP model. And we are preparing tensors there for supervised learning. So it is training as well, and we are using the Adam optimizer itself. And every 200 epochs it is giving me the training results for the base model and the validation results. And after it trains, I am plotting, and as you can see, the data is not underfitting or overfitting. It is almost at par. And the baseline prediction of x1 and x2, so what is the actual x1 line and what is the predicted line, so it's almost close. And the PINN model, we are defining the PINN architecture, that is we are defining the layers, we are defining a soft place, gradients, residual curves, and all the thing, and the collocation as well. Then we are training out here for like 1800 epochs, and again every 200 epochs it will output the accuracy, that physics side of stuff, and all the calculations which we had done. And I plot the results out here, the loss function, so you are able to see this. and their graphs are like almost similar. There is no like too much of there is no underfitting or overfitting. And we are defining an inference and helper to get inference to the entire series basically, and we are predicting out there. And as you're able to see, the accuracy is quite good. And then we zoom out into one particular section, that is this, and you are able to see the graphs on that actual x1 baseline. So baseline is way off, but the PINN is almost in the vicinity. And you have your metrics and the value, the whatever result we got, I made that into a table for easier understanding. And then we can compare that with the baseline and PINN. The RMSEs of PINN is much less. The lesser it is, the better it is. Even the R2 as well. And we do plot all those metrics out here, that is the baseline, the PINN residuals, and compare the models. As you can see, residual traces are lesser compared for that. And for we plot the predictions as well of the velocity and acceleration, what is the real one and what is being predicted. And then we do a sanity check for PINN, which has come out quite good. And we have these different metrics comparison as well for baseline, MLP and PINN. So as you can see, RMSE, MAE, everything is lower of PINN compared to them. So the lower it is, the better it is. So these are some final takeaways, that is like what can you infer from these codes. That is, it respects differential constant, it tends to produce more consistent derivatives, and it can extrapolate more sensibly compared to normal neural networks. And I just want memory optimization, so I just clean up my cache once it's finished. So yeah, thank you for your time. Hope you liked the session.